And recent work and work which is done in particular at the Flatiron Institute, which I've been busy building for the last couple of years. So let's start with a definition. So the quantum many-body problem is really, does it work? Yes. So it's really the physics of many interacting quantum particles, and we see this kind of problem. We have this problem in many different systems. Of course, in condensed matter physics, with electrons in solid, in materials, for example, famously high tensor superconductor. What is this thing saying? Okay, now it's stuck. Huh?
There is a relaxation time. Wait a few seconds.
All right. Okay, thanks. So with high TC superconductors, for example, or in nanoelectronic systems with quantum dots or interfaces, or in these new systems like the Moiré system, which are a bit in between devices and materials. We also have this problem, of course, in quantum chemistry. That's the core of quantum chemistry. In quantum optics, for example, in ultra-cold atom experiments or Rydberg experiments, and of course in nuclear physics. So I would say that the quantum many-body problem has been a central topic in the life of IPHT over the years, with many contributions. I quoted here only a few names of people who have, helped my work and inspired it with their early work, on their work or their books. But of course, I could cite a large number of people in IPHT because this is very close to quantum field theory, and of course to condensed matter theory. So basically, I could quote half of the lab, most likely. So the angle I'm specifically interested in here is not just the theory of quantum many-body problem, but the computational aspects of it. So by that I mean the methods, the algorithms, the concepts that will help us to solve quantum many-body problem on computers. And by that I mean two things. First, clearly doing it on simplified model like the Hubbard model, where I'm sure you all have seen this model before. These things will relax, hopefully. Yes, where electrons hop on a square lattice and experience interaction only in one place. But we don't want to be limited to these models, which are a caricature of what a solid really is. Our goal, and to some extent we can do it today already, is to do ab initio or realistic calculations from first principle. I mean, you give me the structure of a solid with the position of atoms. We start from the Schrödinger equation and the Coulomb interactions, and we can compute the idea, the electronic structure, the response, for example. And the ultimate goal here, if we go to the application, is to do material design. How, for example, do I need to modify this material to increase superconducting temperature, for example? That's the kind of questions. So we want to have the whole spectrum of problems. And in order to do that, I've been busy in the last years to construct, with others of course, a new center at the Flatiron Institute at the Simons Foundation. So this is a research institute which is in New York, close to this Flatiron building here, which contains a couple of centers, people interested in computational method for astrophysics, biology, neuroscience, mathematics, and of course, quantum physics. That's us. It's about 40, 50 people, 4 permanent people, a couple of tenure-track faculties, and postdocs. And the mission of the CCQ is precisely to do what I mentioned before, develop the algorithms, the theories, and including their implementations for solving the quantum many-body systems. So now we are in a position to establish better connection between the Simons Foundation and the CERA in general, and specifically between CCQ and IPHT. And I just want to make a little bit of advertisement, but I'm sure basically everybody knows. We have opened a junior position between the two centers, which we hope to fill soon, to work on these kind of problems. Yes? Center for Computational Quantum Physics. So the ecosystem, I mean, particularly the thing which we are doing at CCQ is we represent on this tree. I hope it's readable, even though it doesn't look very good definition, so I'm going to say it. the physics problems are the ones that I mentioned. I mean, quantum materials, models, strongly correlated systems, up to strange metals, I mean, these kind of models. If time permits, I will show it at the end. And, two-dimensional Moiré systems. So materials on one side. On the other side, everything which is related to dynamics of quantum systems, pump probe experiments when you send a laser pulse to your system and then let it evolve, non-equilibrium systems, up to a system that you can put in gravity interacting with lights. And the core of what we're trying to do here is to develop methods. The roots of the tree basically are the methods, the algorithms, and their implementation into software libraries of some of the most important techniques in the field: quantum embeddings, dynamical mean field theory, and descendants. That's usually what I do. Tensor network techniques, quantum Monte Carlo techniques, electronic structure techniques like GW, for example, density functional theory, and machine learnings. And one of the goals at CCQ is to try to not only have these methods, develop them, but also understand and make them work together in a kind of synergy. For example, we want to use quantum embedding and electronic structure to do ab initio calculations. We want to use tensor network to solve quantum embedding, and so on. And just to connect with what has been said yesterday, I mean, one of the strengths of the IPhT over the times has been, the fact that people were able to work together and do that has been a source of inspiration for me in building a CCQ, and we're trying to have something a bit similar. We are, trying not to have silos of research which do not talk to each other, but something very interactive, precisely to find and understand the synergies between methods and develop them. So instead of doing a catalog of what we can do, I'll show a few more highlights and flash them at the end if time permits. I have chosen to do one highlight, or one set of highlights, related to one technique, which doesn't require a lot of knowledge of condensed matter details on materials, because it's relatively broad audience. And I will use to do that tensor network. So, yes, okay. So the first question is, why can we hope to solve the quantum many-body problem? After all, the quantum many-body problem is exponential in nature. I mean, the Hilbert space is exponentially big, and in many different methods you will face an exponential if you try to solve it. Sine problem, for example, traditionally in Monte Carlo. And the reason is that many of the quantity of the many-body problem, like wave functions or correlation functions, in fact have compressed representations or parsimonious representations, to borrow a term from machine learning, in which sense, of course, they live in a very high-dimensional space, but you can parameterize them with relatively few numbers. There are two big directions that are studied in this idea. One is machine learning itself. For example, you can use convoluted neural network as an ansatz for variational wave function, many-body functions. And there is a wealth of results that have been produced with this idea recently. I will not discuss that. What I will discuss today is the linear algebra version of it in the tensor network technique. So what are tensors? Just to start with basic reminders, I will mean by tensor here an n-dimensional array, some function of discrete indices, I1 to In, that goes from, let's say, 1 to D. Just to avoid any confusion, in other fields of physics, tensors goes with the notion of symmetry, of transformation. Here we're just talking about a bunch of arrays. And I will represent them with a pictorial representation like that, so a box with legs. That's a matrix, A. T is a tensor with n index, and I think it's still for them. And so in this kind of representation, when you contract indices, you just connect the lines. So the rule of the game is we have a big dimensional tensor, and we want to have a low-rank decomposition of it. So what do I mean by low rank? I mean, let's start with a matrix. That's very standard. We know that if we have a matrix, let's say square matrix, we can decompose it, for example, using singular value decomposition, SVD, or others, but into two orthogonal matrices and a diagonal matrix of singular values, lambda 1, lambda n. And in good cases, these lambdas decays very quickly, and you can truncate the matrix and have a low-rank representation of your matrix. At precision epsilon, you keep chi largest single eigenvalues, which means that your matrix will have rank chi, or as we call it, epsilon rank, because it's linked to the precision. So we cut the matrix and we represent it with these two little boxes and contract them. Why we do that? Because we save memory, we save computing time, and again, that's textbook. In fact, there is here a famous book doing these sort of things. For tensor, the situation is a bit more complicated because there are different ways to do it. One popular way is to use matrix product states, also called tensor train, which means I'm going to represent my tensor here as a chain of 3 legs object, except at the boundaries, of dimension chi by the external dimension, and write it in this way. And in good cases, chi is not too big, so that's a low-rank representation of my tensor. But I can use other forms, like trees, for example, like this, or forks, or even 2-dimensional array of tensors. It's called PEPs and meras and have all of these. And I really have a problem with this pointer, but okay. That's the main idea. Now, the canonical use of tensor network in the quantum many-body problem is to represent many-body wave functions. If you take a many-body wave function, psi, and you expand it on a basis, think about, for example, about a spin model with spin up and spin down. My amplitudes are a tensor. They're just a function of my spin index or my electron, if I take the Fock space. And the whole idea of the MRG is to take a variational ansatz for the ground states with a low-rank tensor, typically an MPS or more, which is controlled by the quantum entanglement of your ground state function. So that's a canonical way of tensors. That's what you will use of using tensor. That's what you will see in most presentations. But that is not what I'm going to do today. I'm going to use tensor in a completely different way. So just to contrast, we're not going to go in this direction. However, we can still use this, and that's the opportunity for me to show one of the highlights of the recent work at CCQ, to try to model quantum computers, noisy quantum computer, a NISQ quantum computer. In particular here, the recent article by IBM on their Eagle processor. This kind of tensor can be used to model and understand the experiments. So the initial claim of the paper, which is this curve here, was saying that there was no way to reproduce the calculation of the machine using tensor network on MPSs, because the MPS would give you this yellow curve here instead of the experimental error bar here. But what my colleagues at CCQ, in particular our postdoc Joey Tyndall and Miles Studenmeyer, Bristels, and Matt Fishman have been able to show is that by using a bit more complicated techniques in tensors, a 2-dimensional techniques that mirror the structure of the machine, then they are able to perfectly reproduce the experiment. So in that case, very precise case, disproving the claim of quantum supremacy. So, okay, that's just one highlight en passant. What I want really to show today is how you can use tensor network to compute high-dimensional integrals. Okay? The idea is extremely simple if you think of it. When I have a high-dimensional integral, let's say more than 10, something I cannot compute with quadrature, or a high-dimensional sum, which is the same because I can always discretize my integral, right? A priori, this is a perfect example of curse of dimensionality. If I need to compute this sum here, I will need d to the n operations, look at all elements, and sum. And this is a problem we have everywhere, partition functions like this, diagrammatics. Okay? Now, think about it. If your function can be written as a matrix product state, meaning if f is a product of matrices depending on x1 and xn, which I represent again with this pictorial way. So f is a matrix m1 times n2 times mn, each of them depending on one variable of dimension chi, except at the boundary to make it scalar. If I can represent my function like that with some error epsilon depending on my rank, I will name that epsilon factorizable, then integrating this function is obvious because I have separated variables up to rank chi. If chi equal 1, it's separated. Otherwise, it's, So a very, very naive idea, very simple. How can we use that to compute some of our integrals of interest? Well, first, we need an algorithm given a function that you can compute to decompose it into a matrix product state, which is not obvious. Fortunately, the mathematicians have solved this problem for us, starting with the work of Oseledets about 10 years ago, and more recently by the work of Dolgov and Savostyanov. And they provide you an algorithm, which is called the tensor cross interpolation algorithm, which I will not have time to describe in detail, but I'm happy to discuss if people are interested, that will progressively, by increasing the rank, build an MPS representation for my tensor by evaluating it on a small, quote-unquote, number of points. The number of points that it really uses is n, the number of indices, d, the number of index in one dimension, times chi-square, which is clearly much smaller in practical cases than d to the n. So it basically samples, even though I don't like this word because it's perfectly deterministic, it's not a stochastic technique, the tensor in various two-dimensional hyperplanes. And by doing this and sweeping on the tensor, increasing progressively the rank, it's able to construct a better and better approximations with two characteristics. First, it's a rank revealing algorithm, meaning if your function has low rank, you will find it. If it does not, it will tell you that it doesn't. It will fail correctly, not provide the wrong result. And it will do that with an error estimator, epsilon of chi, that in good cases will decrease as a function of the rank. For example, in this case, 1 over chi to the 4, but that's model dependent. So we have an algorithm that will be able to do that. Yes? So let's show that in a very concrete example. And I want to do that in perturbation, to compute perturbation theory. And I think we were probably the first to use this algorithm in a physics problem, at least in a many-body problem. That's a collaboration that has been done with some people at CEA, in the group of Xavier Vental in Grenoble. I mean, the work was initially started by our postdoc, Philippe Dumitrescu, before he left for a fancy job at Amazon Quantum. So perturbative series are very often underlooked, in our field. People say, oh, things are non-perturbative and we need non-perturbative technique. It turns out, in fact, there is a lot of information you can get with high-order perturbation series. And there's been a renewal of this interest following, in particular, the work of Prokofiev and Swistunov on so-called diagrammatic quantum Monte Carlo, which is a way to compute high perturbation series by computing the high-dimensional integrals by Monte Carlo. And the point is that you can use this series in strong coupling regime, even beyond the finite radius of convergence of the series, using all sorts of resummation techniques, which is not the purpose of this presentation. But one can compute the Kondo effect, for example, or even at finite temperature, the pseudogap in the Hubbard model with exact solutions. For example, let's mention this. There is a nice work that's a collaboration between our former postdoc, Riccardo Rossi at CCQ, and the team of Michel Ferrero at Collège de France. So what I'm interested in here is how do I compute a large number of order in perturbation theory quickly and efficiently. And I will do that in a concrete case, which is a simple quantum dot. So something you can realize in mesoscopic physics, a little island of electrons connected to two leads. So you have here one orbital of electrons with a gate potential that you can change, that experience interaction only on the site and connected to non-interacting leads with a bias voltage. The Hamiltonian is just writing what I just said. There's a bias, a dot, an interaction, and an hybridization between the two. It's one of the simplest problems of quantum matter physics, called an impurity problem. And if I want to compute the expansion, let's say, of the current or the charge of the dot, that's textbook. I mean, it's Schwinger-Keldysh. I can write an explicit expression for it. I introduce the Keldysh contour, double contour, with times u's, u1, un, Keldysh indices plus or minus 1 for the contour, and I have an expression which is explicit for the quantity as a function of time, which is a determinant, sum all the Feynman diagrams using Wick theorem, and I sum all the Keldysh indices, and I have this thing. I just need to integrate it. And until recently, we obtained a lot of results by integrating it using Monte Carlo, but as I'm going to show, we can do it with tensor network along the line I mentioned. Note that this here is a sum, 2 to the n, so it costs O to the n to compute this function. So it's a function which is costly to compute in high dimension. You want to solve that at dimension 10. We can go up to order 30 nowadays with these techniques. And of course, in real life, in real time, this function oscillates like crazy. I mean, in every dimension, because you have oscillations in a real-time problem. the point here, the whole point is that this function is epsilon factorizable, and that was quite a surprise for us. The fact is these functions can be written as a matrix product state, okay, not on time, but on time differences, if I take order time in a simplex of time-ordered functions, function of time-ordered. And that is obtained by the algorithm I mentioned before, so we can use this algorithm and integrate. You don't need to take my word of it. Here is a graph of Q at order 10 as a function of in one random direction. You can see the exact function in orange and the points on the MPS with k equals 30, which is quite small. It's on top in every direction. And we can even benchmark that because one of these problems is integrable. If you take it in equilibrium with a flat bond, there is a famous Felix-Wingman solution with better ansatz. So we can completely benchmark our technique there. And if you look at the number of evaluation of this function you're using, which is chi to the square, you see that chi doesn't really grow with n, which is a very important result. And here is the relative error compared to the benchmark to the better ansatz calculations. It drops like 1 over n to the square, much faster than Monte Carlo, which is 1 over square root of n. And you can basically go to machine precision. Here we go to 10-digit accuracy, including at order 20. So this algorithm, in some sense, learns the sum of Feynman diagrams because it's a learning algorithm with tensors, and you use the tensor form to compute the integrals. And this thing is totally insensitive to sign problem. Some of these integrals can have sign problem, and the average sign of the function 10 to minus 8, it doesn't see a thing, it just integrates. For example, what we can do with this is one example of physical quantity, just to show one, is the differential conductance of the dot as a function of bias voltage and gate voltage. You can see here this structure, which is called a Coulomb diamond, which is V structure, which is related to Coulomb blockade. And here, this structure here is the manifestation of the Kondo effect in quantum dots. And I put here experiments. Experiments have different values, but one value of experiments, and you can see we have the same structure, and we can start to have detailed comparisons with experiments because these calculations are relatively fast now. We can compute all the points, and we can start having detailed discussions with experimentalists. Right. Before I conclude, I wanted to highlight a few more things. I talked about function with n variables, disentangling the n variables, right, with Tans network. What about function with one variable? Can I do something with a simple function f of x? And the answer is yes. And in fact, there's a lot of excitement these days in several groups, including ours, on these techniques, which is called quantics. Lack of better idea, I guess. Tensor network, tensor train. Take function of one continuous variable, let's say between 0 and 1. And I use the decimal representation of x. X is 0.d1, d2, dn, d6, where d is from 0 to 9. Usually it's done in base 2, but okay. Just you can do it in decimal basis. This is a tensor. I can look at this as a tensor where the inputs are d1, d2, d1, d3, d6. And it turns out that this tensor has low rank in many functions. In fact, if you take exponential of x, it's easy to show it's rank 1. It's a very simple thing. So for cosine, it's a sum of 2, so it's rank 2, and so on. So many functions, in fact, a lot of functions, including with discontinuities, with sharp features, with a lot of oscillations, can be represented with this quantum train. And this algorithm can even give you ways to find minima of extremely complex functions quickly if you can represent them. So which function can we represent? Which subset of the functions? How do you use that? People have started to try to use this to represent in 2 dimensions. You can do it with 2, 3 variables to solve PDEs. People are trying to do turbulence equations with Navier-Stokes. What is the representability of this ansatz? We don't really know. I mean, people are working on it. But it's yet another way of using tensor network, which is different, which of course you can try to marry with the previous one. And if I have 2 minutes, I'd like just to highlight very quickly 3 more results, just to show a few results, and then without too much explanations, to broaden a bit the picture. First, I mentioned that there is a strong effort at CCQ doing auxiliary field quantum Monte Carlo, both for model and realistic systems. I just want to flash a very, very nice result of my colleague Shiwei Zhang, who is an expert in quantum Monte Carlo recently, that using quantum Monte Carlo on DMRG to validate some approximation that are able to tame the sign problem in the FQMC on cylinders and then pushing it on large systems to establish, in my view, a high degree of accuracy that the Hubbard model, if you put second neighbor, has D-wave superconductivity, and find all the delicate balance between charge order and superconductivities in this very recent paper. So that's something, if you are interested in more, I'm happy to discuss, just to flash the results here. And since I'm doing quantum embedding and I mentioned ab initio calculations, I just wanted to again show one slide about that. Quantum embeddings, it's a fancy name for dynamical mean field techniques. It's a whole set of methods where we basically remember that solids are made of atoms. So we're going to describe solids in terms of an atom dressed with bars and interactions and all these sort of things. And just to show that indeed today we can do ab initio calculations, here is an example. We have a metal, a correlated metal, which is due not to the interaction U, the Coulomb interaction, but to the Kunz coupling, in fact. It's a multi-orbital material. And today we can compute, for example, Fermi surfaces in these systems with several sheets, self-energies, spin dynamics. This is calculation, this is experiments. This is calculation, the experiment is the blue lines. It's an extremely clean sample, so you can really make very nice laser experiments. This is experiment, this is theory, and there is no adjustable parameter here. It's just an ab initio calculation. And just to mention at the end, because we are at IPhT, I just wanted to connect with what other people are doing here as well. There is an interesting topic these days about Planckian metals, which are a class of non-Fermi liquid metals, which do not have quasi-particles, a maximal violation of Landau Fermi liquids, which have a minimal relaxation time, which is remind us about black hole dynamics. And in fact, there is this ADS-CFT correspondence. You can look at the recent review we wrote with Subir Sachdeva about that. And the fact is that because we have numerical techniques, we can now show that a disordered system, the quantum spin glass of Heisenberg type, disordered SU2 with holes in them, has a quantum critical point. And at that quantum critical point, you have this Planckian metal, which is described by ADS-CFT. And with a very nice linear resistivity, this slow Planckian time. And that result, I worked on that in my PhD almost more than 20 years ago. We only had large N techniques, and in large N, all of that is crunched to zero doping. You can't find the Planckian metal, and the only reason we didn't find them then is we didn't have the tool to solve the real SU2 cases. And now this is routine with the algorithm that we have developed for quantum embedding, and we can use that, find these Planckian metals. And I'm sorry, I've just probably 1 minute late. Thank you for your attention.
Questions for Olivier?
Well, somehow it is more of an observation. You showed us the one-dimensional case using the binary digit expansion and said that continuity is not very important in that. And in fact, if you forget about continuity, there is whatsoever no difference between infinite dimensional integrals and one-dimensional integrals. I mean, for instance, if you have your sequence of binary digits, just split it in two and you transform your one-dimensional function in a two-dimensional function, or in whatever.
But the rank will, if you're not careful, the rank will increase.
Well, probably, but
well, because the point is to have this with low rank answer.
Oh, sure.
So yes. But I'm just saying that for these representations, you can have discontinuities, right? It's not, you don't need to represent smooth function, contrary to orthogonal polynomial, for example. That's what I mean.
But for instance, you could take your 10-dimensional integrals and transform them into a one-dimensional integral and test if it's still low rank. That's something you should do.
In general, it won't, but yeah. That's a catch. So I will keep it like this.
Bien.
Wow. Dangerous, please. Yes. Yes.
Just a curiosity question, say, regarding the simulation or the emulation of the quantum simulation performed by Google. Can you please let me know? I was by IBM?
Oh, yeah.
No, it was by Google or IBM?
No, that's the IBM one.
Okay, good. So the question is, do you have any idea of what could be improved, like trivially, for this MPS method, not to reproduce efficiently or the result that they were able to produce?
So how will this kind of method fail?
What should they improve, in their experiment, so that the MPS and related techniques could not be able or would not be able to reproduce?
Thanks. It's an excellent question, and it's a difficult question. Clearly, I mean, it's not just a number of qubits. The underlying question here, which comes to when would a quantum machine really be efficient compared to classical simulations? That's basically the question. And you need to be in a situation where there is an irreducible entanglement, which you cannot treat by changing the structure of the tensors and treat in this way in this regime. And that's not totally obvious to engineer. But clearly having better qubits would help. Better decoherence. It's not totally obvious. Probably larger system would be more difficult, but we'll see. So it's a very interesting discussion between people who are developing these quantum computers and the simulation, because it pushes people to try new set of tensors and have this discussion.
There were probably already entanglement in there.
Oh, there is entanglement, yes.
So, probably the reason for which you were able to reproduce the result is that noise was there.
Yes, of course. Oh, yeah.
Do you see any benchmark regarding the noise? Any level where beyond some value you would not be able to the same?
Just repeat the question, Olivier.
Yes.
Because
So the question is that we can reproduce that. Well, not we. They can. With this kind of approximated low rank approximation, because there is noise. So you model the fact that you have a noisy problem. We use it by doing an approximation of your n-body functions, right? So the precise question is, how much would you need to reduce the level of noise to be simulable with that tensor? On that, I don't know with details. I mean, we can discuss, but certainly orders of magnitude, an order of magnitude, I would say.
So Pierre Francesco.
Do you have some constraints on the regularity of the function when you integrate it, and how much it's realistic in like hard optimization? I mean, because in general I can use exactly
this kind of thing?
Yeah, because in general I can use this if I just put an xi there to compute the ground state, and there are cases which we know that you cannot.
Absolutely. So the function which we have here is relatively smooth. So the key here, and that's why we use time differences, is that this doesn't like discontinuity. Mm-hmm. If you take a Heaviside function, it doesn't factorize easily, right? So that's why we take time differences, because it eliminates, it puts the discontinuities to the boundary of the simplex, right? Mm-hmm. So regularity is important, but for this kind of diagram, the functions are regular, right?
Okay.
So regularity is very important. However, if you use the other one, with the decimal representations, then you can handle more irregular functions. And if you combine the two ideas, I don't know.
But so if I just take, for example, a spin system, releasing one, it's fine.
Yeah,
it's fine.
You can, for example, in an Ising spin, we also did a 1D Ising problem with long-range interaction, compute the partition function with that technique. It works. So yes, but there are some constraints. But the good thing is, we can't predict a priori if your function will be factorizable. But the algorithm is robust. You can just compute the function, put it in the algorithms, and look. And it will tell you the answer. So you don't need to have an a priori knowledge.
I have a very small question. A priori, your techniques are able to apply to other fields, like high energy physics
What I think first, we try to replace Monte Carlo sum in many of our own algorithms. That's the current thing. But clearly, that's why I chose to present that here, is because you have this kind of problem in many different areas, and so
you might be able to interact with people working in I don't know, physics of reactor. Or
I don't know if I want that, but yes. Yes, but it's a general problem of some high. The point is, some high-dimensional integrals with this technique can be done by this. And we should view Monte Carlo as the backup solution. The next solution if such techniques which are more efficient do not work. So, you know, it's open. But it's relatively new. This is 1 year old. So we try to play with that in various different contexts and see.
One last little question.
I wanted to ask if you checked
Sure.
your technique with quantum field theory Feynman diagrams, because in this case you have what is called HEP sectors, which large momenta. You have your theory is like a massless theory. You have very anisotropic directions in which you feel singularities, infrared singularities. So it is really, really anisotropic. And
Yeah,
I would be curious to see.
The answer is no. What we are doing at the moment is move to lattice problems. So we have start to handle, you know, K-space. But the plain simple answer is no, not yet. One can try. One other thing I could mention, that we are going to release the small libraries with the algorithm, so it's easy to pick it up and try and see if it works. The point is it's relatively cheap to try and fail if it fails.
Good luck.
So let's thank Olivier again.